we can also have improper integrals at endpoints other than infinity. If you have an integral where an endpoint happens to be the location of an asymptote, then we would also need to use an improper integral in order to evaluate that. And what I mean is we would need to change it into a limit in order to evaluate. So let's take a look at an example. So evaluate the integral from 0 to 4 of 1 over the square root of 4 minus x dx, if possible. State whether the integral converges or diverges. Okay, now the problem with these integrals is that they're not quite as visible that you're dealing with an improper integral. So you have to be very careful. The integrals involving infinity is very clear, but here it's not quite as clear that 4, if we plug that in, we're going to have 1 over the square root of 4 minus 4, which is 1 over 0, or the location of an asymptote. So we can't evaluate this integral directly because of that. So we have to use the same approach that we did with an improper integral at infinity. So we can change this into a limit as, say, t goes to 4. Now, one thing that is proper to do is to state whether you're coming from the left or the right, so that you're only on values that are defined for the function. So here we're integrating from the interval starting with 0 going up to 4. So we would be coming from values that are less than 4 but approaching it. So we're on the left hand side. All right, and we'll go from 0 to t then of 1 over the square root of 4 minus x dx. Okay, now let's work on integrating this. Well, one thing we would need to do in order to integrate this, ignoring the limit at the moment, is probably use some u substitution. So u would be 4 minus x, du is negative dx. So what I can do is just pull this negative outside the limit, so just like that. And then I would be integrating from, I'll handle the endpoints of integration in just 1 second. But this is going to substitute effectively to 1 over the square root of u, but that would be the same thing as 1 over the square root, or u to the 1/2, or even better, u to the negative 1/2, which would allow me to use the power rule. All right, so my function has been changed. I also need to change the endpoints of integration. Now, this is not often something that instructors require students to do. However, I do think that it's something that's very important. And it's really rather easy to do. So u is a function, and what I need to do is take the endpoints, which are variables of x, change them into variables of u through this transformation. So essentially, I would just take u and evaluate it at the lower endpoint, 0. So 4 minus 0 is 4. So this new endpoint is going to be 4. And then u of the upper endpoint, which is t, would be 4 minus t. Now, a couple of things about that, just so you know. First off, we've stressed in this class that the variable of integration is important. It defines what type of function these endpoints are, okay? So if I had left these in terms of x and left it from 0 to t, it wouldn't make any sense anymore because now this variable no longer matches the variable of integration. This quick change turns me into a function in terms of u, and everything matches up. And another point is, if you didn't do that at this point in the game, you'd still have to do it later on after you actually do the integration. So you're going to do it at some point anyway, you might as well take care of it early. Now, proceeding, we still have a negative out front, limit as t goes to 4 from the left. Integrating u to the negative 1/2, so we would add 1 to our exponent, so that would become u to the positive 1/2 over that new exponent, evaluated from 4 to 4 minus t. And that would make this a multiplier of 2, so I'm going to make this negative 2 times the limit as t goes to 4 from the left. And here's the cool thing about changing this to u, is you don't have to go back to the variable x. So I don't need to change u into 4 minus x. I can just plug right in. So the upper end point is u, and u is going from 4 minus t, so that would be the square root of 4 minus t minus the square root of 4, which is 2. Okay? Now, as we let the square root of 4 minus t, well, t is going to 4, so as we approach 4 for the square root function, this is going to approach 0, because the square root of 4 minus 4 is the square root of 0, which is 0, so it will approach 0, leaving us with negative 2 times 0 minus 2, which is also negative 2, or a final answer of positive 4. So the value of this integral exists and is positive 4. Here's another. Evaluate the integral from 0 to 2 of x natural log x dx. State whether the integral converges or diverges. All right, so it would converge if we get a real number in the end, or it would diverge if we end up with infinity. So let's see what's going to happen here. So first off, this function is going to be a little bit more difficult to integrate because I have a product of a algebraic piece times a logarithmic. I'm probably going to need integration by parts here, which means that it's probably wise to just do the integration first, get that result, and then take everything back to evaluate for the limit. And I will need to change this to a limit because even though these endpoints aren't infinity, the natural logarithm function is not defined at 0, so it's an improper integral to just plug 0 in. So let's just start off integrating. And you can do this with any problem. It's just usually I reserve it for when the integration is a little bit more involved. All right, so we have x natural log x dx, and in terms of integration by parts, I would let u, so remember the ilate logarithmic comes earlier than algebraic, so I would let u be natural log x. Du then would be 1 over x dx. Dv is just the leftover part, so that's the x dx. The integral of this would be x squared over 2. Okay, so as we integrate, it's going to be u times v, so x squared over 2 natural log x, minus the integral of v du, so x squared over 2 times 1 over x dx. And here's a cool thing. X goes into x squared, leaving me with one factor of x remaining. So that simplifies nicely, which would give me x squared over 2 natural log x minus, there's a 1/2 here, times the integral of x dx. So ultimately, I would have x squared over 2 natural log x minus 1/2 this will become x squared over 2, so you know what, I think I'm just going to save some writing and go ahead and write it as x squared over 4, because those will multiply together. Okay, now, certainly that would involve a plus c in the end, but we are going to use this integral result to evaluate it using the fundamental theorem, so we don't really need to pay attention to that here. One thing we could do, which might or might not be necessary, there is a common factor of x squared over 2 in each of these terms, and that might make it easier to evaluate later on when we do. So let's go ahead and simplify that. Okay, so we have the result of the integral, so now it's time to take the limit. All right, so the limit here is going to be limit as t goes to 0, and this time we'd be approaching from the right, so values that are larger than 0 but going down to 0, of t to 2 x natural log x dx. All right, now the next thing that we're going to do, we've already integrated, so we're just going to plug that result in. So limit t goes to 0 from the right of x squared over 2 natural log x minus 1/2. That would be evaluated between t and 2, which is what we'll do next here. So let's go ahead and write that out. I hope I have space here. So plugging in 2, I would have 2 squared, which is 4 over 2. So 4 over 2 is 2 times natural log of 2 minus 1/2. Plugging in t, I would have t squared over 2 times the natural log of t minus 1/2. And just barely enough room there. Okay, so all of the first part here would be a constant, so that's easy to do as a limit. This next portion, however, looks a little bit more complex. Ultimately, then, the value of this limit depends upon what happens with this portion. Now, there's a couple of things I could do to make things a little bit easier. Like, for instance, if I considered the t squared over 2 distributing. And in fact, I really only have to kind of consider the t squared. So I could just say this is negative 1/2 times t squared natural log t minus t squared over 2. The reason I would do that is this. If I'm letting t go to 0, it's pretty obvious then that this term right here would go to 0. So I could simplify this a little bit, knowing that that portion, the negative 1/2, is going to go to 0. So what I need to really figure out is what happens with this t squared natural log of t. Does it go to infinity? Does it go to 0? It's probably worthwhile coming off to the side and doing that limit separately. So we have t squared natural log of t. And here's the problem. So as t goes to 0, t squared would go to 0 clearly, but the natural log of t is going to negative infinity. So we have 0 times an infinite value, which seems like it should be 0, but sometimes it's 0, sometimes it's infinity, sometimes it's something else completely. You really just have to dig into the limit to see what's going to happen. And luckily, we can actually dig into this limit fairly easily by using L'Hopital's rule. So essentially, if I rewrote this as the limit as t goes to 0, and I'm going to leave the natural log in the numerator, and then switch this into 1 over t squared. And you can mentally evaluate. This is the same thing. If I'm dividing by 1 over t squared, that's the same thing as just multiplying by it. But the reason I might write it that way is the natural log of t goes to negative infinity. 1 over t squared as t goes to 0 also goes to infinity. So now it's an infinity over infinity type, which means I can apply L'Hopital's rule to evaluate this limit. So it's the limit as t goes to 0. And I would do the derivative of the numerator. So the derivative of natural log t is 1 over t. Divide that by the derivative of the denominator. And the derivative of that denominator, you can come off to the side and work that through. You know, if you write this as t to the negative second, that differentiates as negative 2 t to the negative third, which would be negative 2 over t cubed. Now, let's see if we can evaluate this limit. So, rewriting, this would be the limit as t goes to 0 from the right, and effectively changing this so it's 1 over t times t cubed over negative 2. That's going to make this negative 1/2 times t squared, which as t goes to 0, this will ultimately all go to 0. So that limit goes to 0. Which means that goes to 0, so this whole term over here is going to 0. So the value of the limit overall is 2 times the quantity, natural log 2 minus 1/2. And since that's a real number, the value of this limit converges. Here's another example, which is even more tricky. The reason that this is even more tricky is that if you plug in the lower endpoint, you get a real number. If you plug in the upper endpoint, you also get a real number. However, you cross over, when you go from negative 1 to 2, you cross over the point 0. 0 would lead to division by 0, so you have this issue where x cannot equal 0. But it's not that obvious. So you really have to be on alert here to look for these kinds of things. Especially because if you worked this without limits, and I want to point out that this will lead to an incorrect answer. This is going to be incorrect. So I'm just going to let you know ahead of time, and we'll just walk through the details. And actually, let me go ahead and change that into x to the negative third so that we're ready to integrate with the power rule. And we'll do this quickly because I just want to use it as a comparative. So integrating x to the negative third would be x to the negative second over negative 2 from negative 1 to 2. So that would be negative 1/2 times 1 over x squared, so the upper end point is 2, so 1/4, minus 1 over x squared at negative 1, which would just be 1, and I'll go ahead and write that as 4/4. So what do we end up with? Negative 1/2 times negative 3/4. This looks like 3/8. So it looks like a finite value. Okay. Now, properly, and I don't want to say properly, this is correct. All right, so this is, the previous method was incorrect. We integrated over an infinite value, which you cannot do. So here's what we would need to do. We would need to write this as the limit as t goes to 0, going from the left-hand side, I suppose. So from negative 1 up to 0, effectively, of this function, plus the limit as t goes to 0 from the right, so going from t to 2x to the negative third dx. Now we can go about evaluating here. So I've changed it into the sum of two separate limits, which is what you have to do here because you have to see what's happening at that infinite value. All right, so let's try and do this a little bit more quickly since we already know some results here. The integral of x to the negative third, actually, let me just go ahead and pull out the negative 1/2 multiplier. So it would be negative 1/2 times the limit as t goes to 0 from the left of 1 over x squared evaluated from negative 1 to t. And I'm just using the result here, which was negative 1/2, that's the multiplier there, and then x to the negative second is 1 over x squared. All right, then plus another multiplier of negative 1/2, so actually I just make that minus 1/2, limit as t goes to 0 from the right of 1 over x squared from t to 2. Okay, now I actually can pull that negative 1/2 multiplier out of everything. And, I'll come down to the next, I don't know if I have enough space here. So negative 1/2 times, plugging in the endpoints, I would have the limit as t goes to 0 from the left of 1 over t squared minus 1 over negative 1 squared, so that's going to be just 1, plus the limit as t goes to 0 from the right of 1/4 minus 1 over t squared. Okay, now, as we allow t to go to 0, the thing is we have 1 over t squared. So as t approaches that from the left, that is certainly going to infinity. And in fact, if I was being a little bit more careful, I could say it's probably negative infinity. All right, if we're approaching from the left-hand side. Approaching from the right, it would be going to positive infinity. All right, so the thing is that both of these limits evaluate to infinite values. It doesn't really matter if we multiply that by a constant or not, it's still going to be infinite. So this is infinite, and therefore this limit actually diverges. So that's the thing you have to be careful of. If you skip over these kinds of points that you end up with division by 0, you can get a result, and it might look rather trivial to integrate, but you're not supposed to get a result because this limit actually diverges. So you have to be very careful here.